Okay, well, here's the penultimate max min problem I'm going to do for you. And I mentioned that I got some fame from one of these. This one I became famous for, or maybe I should better give the credit to my dog Elvis. My dog Elvis became famous for being the dog who knew calculus. There he is right there. He was on the cover of all sorts of journals and continues to be. He been on probably over a dozen of them, or probably 2 dozen by now. He and I have given talks all over the United States. He died now about 7 or 8 years ago, but he and I gave probably 200 to 300 talks all around the United States, and even over to China and Hawaii and so on. Duke University, Notre Dame, all sorts of places. Pretty cool. And so here's what it's all about. Um, when I first got him, then I took him to the beach, and I'll draw this right in here. Well, let's see. Let's draw it right here. And here's Lake Michigan, which is pretty close to where I live. And I would stand here and toss the ball out into the lake, and he'd run out and get it and bring it back. And then when I tossed the ball out here, I noticed that what he would do is he'd run along the beach a little ways and then go in at an angle to get the ball. And it was very clear from his excitement that he was trying to get to the ball as quickly as possible. So what he was doing was actually solving a calculus problem. That's a real standard problem. It comes in various guises, but it's basically you have two different rates. You can go faster along this route than this one. So you have to either choose. Do you want the shortest route, in which case, or shortest by way of distance, by which you would have to be swimming the entire time, which of course is slower than running, or do you run the entire way all the way to this corner and then swim the shortest amount possible, or do you do something in between? And what he did was he did something in between. So he jumped in, say right there. Here's the corner right here. I tossed the ball a distance X out into the lake, and he chose some distance Y to jump in at this point. And once he jumped in, then of course he went like that. And so instead of running all the way to the corner, he would choose this distance Y from the corner to jump in. And so I took him with me to the beach, and I practiced with him, and I kept throwing the ball off into the lake various distances, and he'd run along, and I first measured the rate at which he swam and the rate at which he ran, and then I had those down, and then once I had those, then I had a big Phillips screwdriver with me, and when he went running along the beach, I ran after him with this Phillips screwdriver, and I plunged the Phillips screwdriver down into the sand at the point where he jumped in. And I always had to kind of explain to people what when they were asking, why are you chasing your dog with a Phillips screwdriver? I said, well, I'm doing a science experiment. So then he'd be swimming towards the ball, and I had already taped a tape measure to the beach right here with a stake. And so I grabbed the tape measure, and I ran out, hustled out to the ball, got there before he did, and I took this measurement, and then I took this measurement, and those were the two that I needed, and you'll kind of see how it all works. So let's kind of go on, and I'll explain it as we go. So first of all, if this distance here is z, and excuse me, this is x and this is y, then, and his r is the running speed, and s is the swimming speed, then how much time does it take him to get to the ball, given that he chooses to jump in right here? Given that he chooses to jump in there, how much time does it take him to get to the ball? Well, first of all, remember that distance is equal to rate times time, And so the amount of time is equal to the distance divided by the rate. If you travel 30 miles on a bicycle and you go at 15 miles an hour, it's going to take you 2 hours to get there. So similarly with Elvis, this distance right here is going to be z minus y. That's how far he's running. So it's going to be z minus y. And then you divide that by his running speed, which is r, right there. That's going to be the amount of time it takes him to do this. And then how much time does he spend in the water? Well, use Pythagorean's theorem. This is x, this is y, so this is going to be the square root of x squared plus y squared. And so there's the distance, and you divide that by the swimming speed, which is s, and there you've got a formula for how much time it takes Elvis to get to the ball, given that his choice is y. So let's go ahead and calculate it. Let's see what we get. So take the derivative, and let's do a couple steps in one. First of all, notice that this is z divided by r. Z is a constant, r is also a constant. So z over r is a constant. The derivative of a constant is 0. So that part's going to be 0. Then you have, basically, effectively, a minus 1 over r times y. Y is your variable here. So since y is the variable, if x were the variable, and I asked you what's the derivative of 5x, the derivative would be 5. So here, the derivative of this is going to be negative 1 over r. Negative 1 over r. This is a good test to see how much you've learned in the course so far. Now what about this? S is a constant again, so we can leave that out front. And now we've got, what? X squared plus y squared all to the 1/2 power. What's the derivative of that? X is a constant, y is a variable. So you're going to have to use a chain rule. So it's going to be 1/2 times the quantity, x squared plus y squared, to the minus 1/2, all times the derivative of the inside. Derivative of a constant is 0. Derivative of of y squared is 2y. There you go. So there's the derivative. Now we want to set that equal to 0. We want to find out what value of y will give him the minimum time. So let's do a little work here. We can cancel this with this. And if we set this equal to 0, then we can bring this over to the other side, and we're going to end up with 1 over, let's see, well, not 1 over, y over s. This is downstairs. Notice that's a negative exponent. Okay, you see that? Y over s, this is all being multiplied. This is downstairs, and this is going to come over to the other side. Once we set it equal to 0, then we can bring this over to the other side. It's going to be equal to 1 over r. So now, what can we do? We can multiply both sides by r and get r over s times y, and bring that up here, and then bring this over to the other side, is equal to square root of x squared plus y squared. So now we want to solve for y. How do we solve this for y? It's a really nice algebra problem. I guess, do you see, you're going to have to break things up. You want to break them up as much as possible. This is not equal to, remember what we learned the very first day? 4 square root of 3 squared plus 4 squared. Is that equal to 3 plus 4? It better not be, because 3 squared is 9, and 4 squared is 16, which is 25. The square root of 25 is 5. So no, they're not equal to each other. So you can't just get rid of the square root. But what you can do is to square both sides. So if you square both sides, you're going to get that right there. And now you want to solve it for y. So you bring, let's kind of do this jobby here. So we're going to get r squared over s squared y squared minus y squared is equal to x squared. Now we can factor the y squared out. And finally, we can solve it for, let's go ahead and drop all the way down here. Y squared is equal to x squared divided by, I'm going to write it as r over s quantity squared minus 1 squared. Do you agree? That's the same as this. And 1 I can write as 1 squared. And the reason I do that is because back in our algebra, I think at some point we refreshed our memory on this, that a squared minus b squared, that can be written as a plus b times a minus b. So this is equal to r over s plus 1 times the quantity r over s minus 1. And finally, take the square root of both sides, and you get y is equal to x over, I'm going to write it as the square root of r over s plus 1 times the square root of r over s minus 1. So there's the answer. There's the answer. And if you want to, you can easily find my paper all over the place. There's all the paper and the original paper and others. It's just Do Dogs Know Calculus? Go ahead and check that out. You can also put in, if you just put in Elvis, that was his name, and calculus, and Corgi, that's the kind of dog he was. You'll find all sorts of articles about us there as well, okay? So, as I say, he became very famous, and so on. What's so interesting about this answer, and I'll stop here as far as this particular problem is concerned, but there's just a lot of interesting stuff here, is that here's the question I would ask people. I'd say, suppose when I stood right here and threw the ball right here, the best spot for Elvis to jump in was that spot right there. Suppose that that's the case. Then, what should Elvis do if instead of starting here, I back way up another 15 or 20 yards and I still throw the ball here? So I back up further but still throw the ball. What should Elvis do? Should he still jump in at the same spot? Should he go forward a little bit? Should he go back the same distance that I went back? Or should he go back a proportional distance? And 90% of the people would say, well, he should probably go back a proportional distance. That's certainly what I thought. But look at this answer. This answer shows us that our intuition is wrong, because in particular, there's no z in this formula. So his choice of where to go in, to optimally go in, only depends on how far I throw the ball into the water and his running and swimming speeds, but it doesn't depend on z. So it doesn't matter whether I start here, 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 or 10 miles away, he still jumps in at that spot. And that's just one reason why I think this problem is so interesting, because it shows the power of mathematics. It shows the power of calculus, that your intuition tells you one thing. I'd have 90% of the people in the room all agreeing. So if you went with the crowd, if you either went with your own intuition or if you went with the crowd, you'd have one answer, but mathematics cuts through all that stuff and says you're wrong, you're wrong, you're wrong. And that's the power of mathematics. That's the power of a formal education, where you learn some of this stuff that has been handed down through the centuries by Newton and Leibniz and Cauchy and all sorts of others. Bertrand Russell, all sorts of just great names have brought calculus down and mathematics down to us. So as I tell them, I say you can learn an awful lot about life by joining the military, traveling the world, getting a job, going living on the streets. There's all sorts of valuable lessons you'd learn about life by all those things. But you learn some of this really uniquely powerful discoveries, the most powerful and beautiful things that the human race has ever discovered. You find those out through kind of a formal education involving well, I love everything. I love poetry and English and history and all that stuff, but science and mathematics certainly is probably the top of the list. Good stuff here, good stuff. So anyway, that's this particular problem. As I say, check that out. I wrote a follow-up article. Do dogs know bifurcations? And that one actually won a math award. It's called the George Polio Award. That one asked the question, what should Elvis do if now, instead of starting on the beach, we start in the water? And if I throw the ball just a little bit away and he's with me in the water right here, it seems reasonable that he should, probably swim right there and get it and bring it back. If I throw it a long distance away, then, well, if he really knew what he was doing, he would probably go down here, come along here, and go back there. And that became a really interesting mathematical puzzle for a while. Some people thought he was going to do this and whatever. I actually did it with him, and he actually came and did all this and went back into the water. So that's called a bifurcation problem, because he has one of two distinct choices. Either it's this or it's all the way to the beach. There'd be no reason to go halfway to the beach. That wouldn't get him any advantage at all. So you have two very distinct courses, decisions to make, and so it's called a bifurcation. Bi meaning two. This is the word from which we get the word fork. So you go one way or the other. So lots of good stuff there. Other articles as well. So I'll stop it there, but I could go on for hours on Elvis and Do Dogs Know Calculus. Okay, that's good.